Thank you. So this is using fibre brag gratings again, just rather a different structure to the structures that we've just been looking at. Briefly about my company, it's 16 years old, still a very small company because the market grows very slowly. Our main markets are the energy sectors, oil and gas and renewable energy, but also aerospace and several other industrial markets we work in. The fibre brag grating, I think many of you in the room know what it is. For those of you that don't, I can just say it is a fibre optic sensor. It's written into the core of a standard single mode telecoms grade fibre. The sensor is inscribed by two very intense UV laser beams, and the result is a sensitive location which responds to temperature, and it also responds to strain. So the way you can make a system using this technology is you have a laser which sits inside this blue box up here. It shines light down multiple fibres, and wherever there is a fibre brag grating inscribed, you get a wavelength of light reflected back, which gives you information about the strain or the temperature on the fibre. And then that data is passed to a computer, which does all the clever stuff. Okay, this is a little demonstration of how the technology can work at high speed. So this is a fibre brag grating it's attached to a tuning fork, and you can see there as you squeeze the tuning fork, the fibre brag grating strain is detected. And then when the tuning fork is struck, it rings at 500 odd hertz. This data is being sampled at 10 kilohertz, so you can now see on the screen 2 seconds of data captured at 10 kilohertz. And when you can zoom in and see the raw data, you can see the type of resolution that we can get at that speed. Now, using that capability, we looked to this machine, which is a subsea twin screw pump. It sits down on the seabed and pumps hydrocarbons to the surface. The picture of the subsea field is offshore Brazil. So here the customer wants to monitor the pump because it's sitting in very deep water, sitting in 3 kilometers of water. It's a very critical asset, and the cost of failure is very high. If the pump fails, your bill is about $1 million a day. Firstly, you've got typically $100,000 a day lost production because you're not pumping oil, but also the cost of the service vessel that you need to hail to exchange the pump is chartered, and the charter price is about $900,000 a day. So you really want to know your pump is going to fail, and you exchange it before it fails when that service vessel is nearby. The reason the client wants to go for fibre is that he recognizes he's in a very harsh environment. He doesn't want to put a condition monitoring system down there which is no more reliable than the pump that he's trying to monitor. So he's recognized the opportunity to have a condition monitoring system where you've got just fibre optic sensors in the harsh environment, which we believe are very reliable, and then the electronic part of the system is up on the surface. And in this application, we have 3 kilometers depth of water, and then we've got an 11-kilometer tieback, total of 14 kilometers between the instrument up on the FPSO and the sensors down in the pump. Okay, we monitored many different things. I'm going to focus on the bearing monitoring, but before we do that, I'll briefly show you the other things we measured. We measured some temperature inside the electric motor that drives the pump. We had 2 fibres going into the stator windings. Each one had 9 brags on, so we're measuring 18 temperature positions. We measured the pressure and temperature inside the pump to make sure that the lube oil was pressurized and circulating properly. This is using a standard brag grating based diaphragm pressure transducer, the type of gauge that we put in oil wells to measure pressure in oil wells. We also used a fibre brag grating accelerometer. So this little guy here down in the bottom left-hand corner, it's about 20 millimeters in diameter. We packaged 3 of these in a 1 atmosphere can and sat it on top of the bearing housing to see if we can see any vibration on the housing, which was picking up damage on the bearing. There was actually no vibration that we picked up because we thought the bearings were in very good condition. As we would have expected, they were brand new bearings. But we also looked at the bearings in a different way. We chose to put fibre around the outside of the bearing. So we machined 2 grooves in the bearing outer race, and we put fibres in those grooves with a number of fibre brag gratings in each fibre. So we've got a number of different strain measurement points. As you run the pump, you've got load going from the shaft through the bearing housing, and where it passes our fibre, which is in the bearing outer race, we have strain, and we can calibrate that strain against the load. And this is a plot of load on the vertical axis versus time on the horizontal axis. So this is one afternoon of testing, and we're recording about 108 kilonewtons of load on the drive end bearing, somewhat less on the non-drive end bearing. The 4 reference points at about 6 o'clock, we're comparing the load with the load predicted by the FE model, and we correlated within 5%, which means it was a very good FE model, and it also means that the load monitoring system is accurate. The condition monitoring is shown here. This is the raw data from one of the sensors. So the peaks that you're seeing is the signature of each of the rolling elements passing the particular strain sensor that we're looking at. And as you can see, one of them circled in red has a rather peculiar signature. All the others are nice and smooth sinusoidal type peaks, and the other one has got a little glitch in it. So we put some processing on that data, and we did the same processing on 2 bearings that we're instrumenting. The one on the left didn't have this feature, the one on the right did. So here the horizontal axis is again time in hours. The vertical axis is microstrain, so it's from 0 to 5 microstrain. Very small signals. We're looking at the noise on top of the signal to give an indication of the health of the bearing. So very little noise on the left-hand bearing, quite a lot of noise on the right-hand bearing. So it's clearly detected something. And when we first saw that, we thought the bearing was about to fall to pieces. But in fact, when we had finished running the pump, we disassembled the pump, took apart the bearing, and we found a scratch, which was 3 millimeters long and 2 micron deep. And we saw it with this much clarity, and we happened to see it through a 10-kilometer fiber because we wanted to demonstrate that we could properly do remote condition monitoring. So on that test, we managed to detect a scratch on the bearing there, which was just 2 microns deep. And the bearing was located, well, in the application it will be located down there, and our instrument will be located up there some 14 kilometers away. So then we decided to set up this little demonstration rig, and rather than showing you a video of it, I can show you it actually working properly. So here it is over here. So this rig has 2 bearings on it. This one on the left has a damage feature. It's some of you in the front row might hear it knocking. This has got a little dent in the outer race. The one on the right has got no damage, so it's relatively smooth. The plot's up on the screen. Can we see the PowerPoint screen again? Okay, thank you. The white trace on the top is the signal from the good bearing. The red trace on the top is the signal from the bad bearing. Down the bottom, we have the load on the bearings, which is calculated from the amplitude of the signals on the top chart. So if I increase the load on one of these, you can see the red line has gone up. The load, which is measured on the right-hand side in kilonewtons, has just increased. If I do the other one, that's the blue line going up. So we've got a calibrated load monitoring system. The condition indicator, you can just about see, in fact you can't see very well at all. You have 2 lines on the bottom chart. One is the red one at the top, and then there is a white one which is just about visible on the bottom of the chart. What that's doing, that's looking at the noise level on the strain data. The bad bearing, which is the one with the red line, and that's telling us we've got a lot of noise on that signal, therefore we got poor condition on that bearing, we got damage on that bearing. The white one, which you can just about catch at the bottom of the plot, that's the good bearing, very little noise, therefore good condition. Okay, that's what I wanted to show you. Also to tell you that we're extending this condition monitoring of bearings to various other platforms. So we've got a project running at the moment where we've got some aerospace vehicle bearings being instrumented, and we've got another project for a very large marine bearing, but many other bearings in very harsh environments that need monitoring. So we see this technology as very opportune for those applications. Thank you very much.
Thank you very much.